Bom dia. Welcome back to the geometry section. I just have a small announcement to make regarding the we're organizing together with the PDE section a dinner. So if you received the email in that regard, please try to make up your mind if you can come or not as soon as you can and let us know, okay? So our speaker today, it's Jacob Bernstein from Johns Hopkins University, and he's going to talk about surfaces of low entropy.
Okay, so first of all, I'd like to thank you all for being here so early and to thank the organizers for the invitation to this colloquium. Okay, so I'm going to talk about some joint work with Lu Wang, who's at the University of Wisconsin. This is sort of an ongoing project we've done over several years. Okay, so the first thing I want to say is, what do I mean by this word entropy, which of course is a very overused word in mathematics. So for me, it's going to be some kind of quantity, or at least we have some kind of abstract point of view where it's a quantity that has sort of three properties. And then I'm going to give a concrete definition, and we're going to sort of see the three properties hold. So the first property is it should be invariant under sort of natural symmetries. Right, so the entropy associates some value to objects in some collection, and maybe there's some symmetries of the objects, and it should be invariant under the symmetries. The second kind of property we'd like to see is that somehow the quantity is monotonic under some kind of heat flow. So again, we'll make this concrete in a second, but for the moment there's some kind of heat equation or heat flow, and the quantity should be monotonic under the heat flow. And then the third property is that somehow the extremals, so the objects on which the entropy is extremal, an extremal value, they should somehow be the least complex. So the extremal have right, so we want to argue that the entropy is sort of measuring some kind of notion of complexity, and again, this is kind of these three properties we want the entropy to have. So these are sort of, okay, and the goal, or not the goal, but rather we want to, specifically we're going to want to, we want a notion of, say, entropy, which I'm going to denote by lambda of sigma, that we can associate to each. So here, this is a hyper. Okay, so we want to consider hypersurfaces in Euclidean space. So I usually will just drop this and talk about surfaces, and we want to associate this this quantity lambda sigma, which will be the so-called entropy, and we kind of hope these properties hold for it. Okay, so how do we do that? Well, the first thing we're going to do is we're going to consider an associated quantity, which we consider the Gaussian area, right, for sigma, and we're going to define this to be a sort of weighted volume. So there's a normalizing factor depending on the dimension. So basically, it's the sort of volume of sigma, but we put in this Gaussian weight. So notice this weight. This is sort of measuring the distance to the origin squared, and so this decays very rapidly. So for instance, this quantity is finite for non-compact surfaces as long as they have reasonable volume growth. And indeed, we compute the normalizing factor is chosen so that if we look at, say, the plane at height t, then this is e to the minus. Okay? So we first of all observe that this quantity obviously is not an entropy because it's not even invariant under translational symmetry. This is not. Okay, so the idea, and this was at least written down first by Kolding and Minicosi. So is we want to sort of make this quantity invariant in the simplest way possible, and then maybe pretend that that's this notion of entropy. So they define lambda sigma as to be the supremum over all possible dilations of the surface and all translations of this Gaussian surface area of Okay, so what this means is we just take a surface and we consider homothetic dilations and all of those taken together and all possible translations of the surface. And then we compute the Gaussian area, and the supremum of those values is what we call the entropy. Okay, so it's obvious is that the entropy is, just by definition, is it doesn't depend on dilating or translating the surface. It's also pretty clear because of the rotational invariance of the weight that if you act by an orthogonal Okay, so this is to say these are all the symmetries we expect of Euclidean space. So this is to say that this implies that entropy is invariant. So at least our first property holds. Okay. And as a remark, just a simple calculus exercise from this tells us that the entropy of any plane or any hyperplane is then 1, right? Because that's the maximum value of this guy. And we can use the symmetries to our advantage to say that that's the only interesting situation. Okay, so that's the at least we've checked 1. So now we need to think about this property 2. And the point here is that we have a natural heat flow for hypersurfaces. So we recall, and I'll say, I mean, we've seen this yesterday, so I won't say anything more about it now, but recall we have the so-called mean curvature flow, is a natural so it's a natural geometric nonlinear heat flow on surfaces, or for surfaces, right? And there's this very important fact about the mean curvature flow called the Huysken monotonicity formula, which is sort of a parabolic analog of the usual monotonicity formula for minimal surfaces. And this guy, if you unwind the definition, you can see that actually the Huysken monotonicity formula is going to imply that the entropy of a mean curvature flow is basically non-increasing along the flow. Okay, so in other words, the entropy doesn't increase along the flow, and so then we see that we do have a monotonic quantity under some natural heat flow. So this is to say that, so at least, and again, this is why maybe this is a natural thing to start with from the beginning, is you look at this this monotonicity. So this, of course, implies sort of property 2 holds. Okay. And then the final observation one makes is that for any hypersurface, and we really don't need to assume a lot about this. Like it could be, it doesn't even need to be proper or embedded, but any sort of reasonable notion of hypersurface, we have that the entropy is actually bounded below by 1, okay, which is, of course, the entropy of a plane. So in other words, the sort of absolute minimum possible value of the entropy is achieved by the planes, and the planes are, of course, the simplest possible surface you can think of. So this is, in a sense, implies 3 holds. And again, the reason this is true is just it's very simple, but if you think about it, like if you pick a point in the surface and you consider the sort of blow-up of the surface around that point, right, because we're smooth, this converges to the tangent space at sigma, right? And if you go back and look at the definition, this sort of tells you that if you just pick a sequence, of blow-ups and, the appropriate translations, that actually the entropy has to be bounded below by 1, okay? And another observation, which I'll just say in words, if you think about it, if you expand your class of surfaces to allow, say, like points of self-intersection, at any sort of point of self-intersection, if you do this blow-up analysis, you're going to get more than 1 plane, right? So that would mean the entropy would be at least 2. So it's a useful fact that if the entropy is below 2, you have to be embedded. Okay. Okay, so this implies, of course, 3 holds. Okay, so all of these are relatively trivial, except maybe this one. But what the purpose of this talk is that we've worked here in the class of all surfaces in some sense. What's amazing is that if we restrict to the class of closed surfaces, so compact and without boundary, in fact, these two are obviously still going to be true, but this actually is also true. And this turns out to be highly non-trivial as a fact. Okay, so let me move on to our main results. Okay, so now we're going to always consider right, and closed means compact and without boundary. Okay? And so the first thing is, before we say anything further, we should think about what are the simplest closed surfaces and what are maybe their entropies. So what are the simplest closed entropies? Well, the simplest closed surfaces, of course, are going to be the round spheres, right? So what one can compute, and again, it's basically a calculus exercise, is that the entropy of a round sphere is actually the Gaussian surface area of the sphere centered at the origin of radius 2n. And these numbers are important, so we're going to give them a name, lambda n. Okay. So this is, again, a calculus exercise I can leave to you. Right? We use this invariance properties and just the definition. And what's important is that this number, these are sort of have been computed. So Stone, several years ago, computed in his thesis, I think, that the exact values of these lambda n for every dimension n, and they have a closed form involving gamma functions. But for our purposes, what's important is that we can put them in a sort of monotonic order with respect to the dimensions. So okay, so the first value for the unit circle is less than 2 and bigger than 3/2. As you go up into dimension, the values decrease, and eventually they limit to the value squared of 2, which actually, if you're familiar with the subject, is interesting because this is the density of the generalized Simon's cone as the dimension goes to infinity. And these are all bigger than 1. Okay? So the idea from our sort of principles of entropy that I mentioned before is that we would expect maybe that if we restrict to the set of closed surfaces, perhaps the extremals are actually achieved by these guys, which should be the simplest closed. So that intuition leads to the following conjecture due to Colding, Ilmanen, Minicozzi, and White. And they conjectured basically that if So they conjectured that this is true, that these round spheres are the extremals for the entropy. And in fact, you can make a little bit further, you can make a rigidity, and you have equality. Basically only for a round sphere, okay? And I should say you should expect something like this rigidity to hold here too, but it's a little bit more subtle because of the non-compactness. Okay, so this is the conjecture, and so this was the starting point of me and Lou's work. And I should say that Colin, Ullman, and Minicozzi-White, they proved this. They made this conjecture, and they proved it for a special class of closed surfaces called self-shrinkers, which I'll get to later. Okay, so our first theorem, this is myself and Wu Wang. So this is true for the following dimension ranges. Okay. So we prove it. We proved it for all dimensions, but all ambient dimensions between 3 and 7. Okay. And so our intuition was correct. And I want to make some remarks. So the first one is the n equal 1 case. This follows from work of Grayson plus a. Okay, so as I said, there's this connection with the mean curvature flow, and it turns out in the ambient dimension 2, the curve shortening flow is very well understood, specifically using work of Grayson and Gage Hamilton. And it immediately, once you formulate this problem, you can prove it using their work, which preceded the formulation of the conjecture in the n equal 1 case. The second remark is that we use, in our proof, we used, at some point, we used the regularity theory of stable minimal surfaces. Right, and this is why. Right, so of course that regularity theory breaks down when n is at least 7 or higher. So at some point we need to know something is smooth, and we prove the smoothness using this regularity theory. So recently, Jonathan Zhu he showed we could you could extend our method. Okay, so in other words, he showed that you didn't really need smoothness, you just need a small enough singular set. So in fact, everything we did works in every dimension. Okay, so in fact, now the conjecture is completely true for every dimension by his work. The third remark I just want to say is, again, our proof in the end is sort of parabolic, which will be analogous to this. But there's a lot of formal similarities. So if you think about what this problem is asking, you're trying to minimize a functional that's defined as a maximum. So there's a kind of min-max interpretation of the problem. And so you can sort of make connections with the Willmore conjecture. So in fact, Ketchevar and Zhao, they sort of used the Marquez-Neves approach. Sort of min-max. So they proved. Okay, so they did this after our work, but it's a different approach, and I mean it's interesting that it works, except for it doesn't seem to work in genus 1 for some reason. So. It's a bit strange. Okay. Okay, so that's our main result in some sense. But once you pose this question, there's a number of kind of natural follow-up questions, which is what happens when you're not at this lowest value, lambda n, but what happens if you're near the lowest value? Could you possibly say that your sigma is simple in some weaker sense, right? So you're not the simplest surface, but maybe you're almost simple. And so we have a number of interesting results along those lines. So we have a kind of topological result. This is due to myself. So okay, so our proof here only works for 2 or 3. Then sigma is diffeomorphic to the corresponding round sphere. So in other words, if you have any non-trivial topology, then your entropy actually has to be, Okay, so if your entropy, right, there's a gap between the entropy of the sphere and the entropy of the sphere 1 dimension lower. There's a non-trivial gap there. And so if you're in that gap, so you're bigger than lambda n, but you're less than lambda n minus 1, then, in fact, you have to be topologically a sphere, at least in dimension 2 or 3. Okay? And let me just say in words, I mean, the proof in n equal 2, we use a kind of classical mean curvature flow. Already in n equal 3, we need to use a weak mean curvature flow. It's much harder. And it's not clear what happens in higher dimensions. So that's open. Okay, so that tells us that really if you're near the bottom of the possible entropies for closed guys, you're actually kind of simple in a topological sense, which is sort of remarkable because this entropy is a very weak thing, so it's surprising it sees the topology at all. The final result I want to just mention very briefly is a kind of analytic rigidity. Right, so we have this stability, we have this rigidity result that says if you're actually at the entropy of the sphere, you are the round sphere. So you might ask if you're extremely close to the entropy of the sphere, how close, you should be probably close to the sphere, but the question is in what topology. So we proved the following result, that, at least in dimension 2, which said that for any epsilon greater than 0, there exists a delta greater than 0, so that if you have a closed surface and its entropy is less than the entropy of the 2-sphere plus delta, then in fact you're close in Hausdorff distance to some sphere. Right? So you can get, so we have to of course, there's a scale invariance in this translation invariance, so you have to mod out by that. But ignoring that, this is Hausdorff distance. So this is a kind of C0 distance. So in other words, if you're near the sphere, you can actually make in entropy, then you're actually near the sphere in Hausdorff distance, or near some sphere in Hausdorff distance. And this is sort of surprising, just if you think about it, because of course, you could think about like the unit sphere with a very small little neck, and because this is so small from the point of view of area, the sort of Gaussian area of this guy and the Gaussian area of the sphere is very close. But of course, their Hausdorff distance is very far. And the key is that because here you have this sort of, it looks kind of like a cylinder, which if you blow up, it means it should look kind of like the entropy actually lambda 1. So that's the idea. And then I'll just say in words, my student, Shengwen Wang, so no relation to Lu Wang, he actually was able to prove this in all dimensions. But it's a much more subtle argument. It's a different argument. So this is now true also in every dimension. Okay. Okay, so let me now, in the last little bit, just give a kind of idea of the proof, or some idea of the proof. Okay, and let me start actually with the simplest situation, which is the n equal 1 case. Okay, so we're going to look at curves in the plane. Okay, so the idea is, let's suppose we start with let's suppose this is our sigma. Okay, and let's call this sigma naught, and let's consider the curve shortening flow, which is of course the one-dimensional mean curvature flow. So we're going to get a flow sigma t. Okay, and the point is, here the idea is the mean curvature flow. You're just moving each point in the direction of its mean curvature vector, right? So, where it's curved this way, the mean curvature vector points inward. With this place, it's pointing outward. And we're just going to evolve the curve in the direction of the mean curvature vector. And the idea is, a special feature of the curve shortening flow is the fact that any closed curve eventually becomes convex in a finite amount of time. So this is a result of Grayson. Right? So he says that there's eventually, you can imagine this part is shrinking in and this part is sort of expanding out. So after a finite amount of time, there's some t convex where sort of your curve has somehow shrunk in, and it's moving very rapidly here, and it's barely moving here, but now it's convex. So here we have sigma, right? And this is in a finite amount of time. And then you can use a number of methods. Then it's not hard to see, or now it's known, but that if you start with a convex curve and run the mean curvature flow, then in a finite amount of time, you get this is a so-called round point. And this is at this Ts, which is the singular time. And the point is, what this really means is that this is to say that sigma t is equal to and let's say this is at some point ys, which is the singularity. It's okay. So the idea is as to say this is a round point, it means it looks like the point plus a shrinking circle plus some error, right? And the observation I'll just make is this itself is a mean curvature flow. It's a special mean curvature flow that moves only by homothety. And the point is, we know by the monotonicity formula that the entropy is not increasing along the flow, right? So we have by the Huysken monotonicity that the entropy of our initial guy is greater than or equal to the entropy of sigma t, right? And so then we can just say that right, we can just say that the entropy of sigma naught, right, is greater than or equal to the limit as t approaches the singular time of the entropy of the sigma t, which of course our surfaces, we don't care about, we're allowed to translate and dilate, so we can just, this part is an error, and we end up basically with, by taking the limit, we get, okay, so that gives us the lower bound. And in fact, one of the things is this is, to think about the rigidity, this is strict unless we have this, Okay, so in fact, we see that we actually have a strict inequality unless we're actually equal to a round sphere. Okay, so that's the proof in one dimension, and we see that it's sort of very closely, the way the proof works is we really want to understand singularity formation, because then we can go back and say something about the original guy. And so the way the proof works in higher dimensions is we still need to understand okay, so in higher dimensions, so for n, we need the same idea, but there's two issues. So the first issue is here we have only one singularity model in some sense, which is the circle, but the problem is in higher dimensions there's many more Okay, so there's many more singularity models, so there's no hope of classifying these without additional hypotheses. So this clearly is a difficulty. The second problem, which is more subtle but somehow turns out to be very key to the proof, especially when n is 3 or higher, is that here we have the flow is smooth until it disappears, where it becomes singular. But as Haotian mentioned last time, there's these neck pinches in n bigger than or equal to 2. And so there's a possibility that the flow becomes singular without disappearing. Okay, this is this kind of idea of a neck pinch, right? And so this turns out to actually be, I mean, it may not appear at first to be important, but this turns out to be somehow the key idea, because somehow, as we eventually showed, singularities that have formed where the flow disappears have better properties than arbitrary singularities. But the idea is you can't see such singularities unless you're allowed to flow through singularities, which requires some kind of weak flow. Okay, so that's a technical aspect of our proof. Okay, so what are the singularity models? Let me just say. So okay, so the point is this Hughesky monotonicity implies that these singularity models are exactly surfaces, say, gamma, satisfying okay, so the mean curvature vector of the gamma plus the 1/2 of the normal part of the position vector is 0. These are called self-shrinkers. Right, so this is a kind of minimal surface type elliptic PDE. And if you have a gamma that satisfies it, then it turns out that basically, this is equivalent to the flow minus T gamma, a mean curvature flow. So in other words, it's a mean curvature. This means that this associated flow is a flow that moves only by dilation. And basically, the idea is it's the same picture in some sense as in the 1D case, is if you start with, say, let's say we look at something like a neck pinch, and we run the flow, so it becomes singular, say, at this point, right? And what you can sort of roughly show is that there's always going to be a way, if you sort of zoom in near ys, that the flow, this is sigma t, near the singularity is going to look like ys. This is ts. Well, let's just say approximately. Okay? Right. And again, what this means is near this, if you look closer and closer to the singularity, you look more and more like this. Again, strictly speaking, this is not quite true, because this is a very important technical point. This is only true along a subsequence of times approaching the singular time. If you choose a different subsequence or a different sequence of times, it's possible you get a different singularity model. So this is this question of uniqueness of tangent cones, which is very subtle. Right. So. Okay, so but again, the idea is that, right, the idea is that the entropy, let's say this is, the entropy of the initial guy is, of course, by the same token, bigger than the entropy of the singularity model, right? So it suffices to try and understand the singularity models. And as I said, in general, to get any proof, we have this problem of too many singularity models, which I don't have time, but trust me, there are a lot. Nevertheless, in n equal 2, we actually do have a classification of singularity models where their entropy is low. So we have the following theorem, which follows from work of Kolding, Illman, and Minicozy and White, work of Brendel. It's a sort of synthesis of all these results, and work of myself and Lu Wang. Okay, so when n n equal 2, and gamma, right, so it satisfies this equation, has so if you have entropy below that of the unit circle, then up to rotation, you actually have only 3 possible models. So there's the plane, which actually is not a singularity model. You can see it satisfies this equation, but it's not what a singularity. You can get the cylinder, or you can get the unit circle. So there's actually only 3, right? So in other words, what happens is that you have basically the plane where the entropy is equal to 1. Then you have the circle where the entropy is, right? Then you have, it's at the cylinder where the entropy is lambda 1. And then you have there's a bunch of stuff up here, which some has been rigorously constructed and some just numerically. But there's a lot of things here. But in fact, in this bottom, it's very simple. And the point is, this is not a singularity model. So the idea is when you look at, say, dimension 2, if you start with a surface and start running the flow, you know that closed guys have to become singular in finite time. That's a very important property of, that's really the only place closed is being used in the proof. But it becomes singular in finite time, and so it has to have some singularity model. So it's not the plane, so the next lowest one is the sphere. So that's how you get the lower bound. And in fact, if you're below lambda 1, you can then see the only singularity model is modeled on the sphere. So you're exactly in a picture like this, where you have a sort of way to connect the surface to the two-sphere. So that actually proves the topological result in that case. But of course, in higher dimensions, I really want to emphasize this is very much a 2-dimensional result. And the reason for this is this result of Brendel, right? So how does the proof go? Let me just say it in words. The idea of the proof is what Kolding, Illman, and Minkowski and White originally proved was if you have a closed self-shrinker with entropy, this entropy bound, then you're actually topologically the two-sphere. So they didn't prove that it was geometrically the two-sphere, it's just that it was topologically the two-sphere. Then what Liu and I proved was that if you have a non-compact guy with this entropy bound, then you were topologically a genus 0 surface. So you couldn't have genus, but you could have maybe ends that were like a cylinder would be genus 0, or the plane is genus 0. So then what Brendel proved, and both of those results that Kolding, Minkowski, Illman, and White, and myself and Lu Wang's, those have analogs in higher dimensions. But what Brendel proved is this sort of remarkable fact that if you're genus 0, which our entropy assumption implies by our work, if you're genus 0 and embedded, which is again enforced by this entropy bound, then in fact you have to be one of these 3 guys. And that's very much a 2-dimensional result as far as I know. So, so in higher dimensions, you would need other ideas, and we developed them based on the weak flows, but it's a much, much more subtle issue. And again, the idea is somehow the singularities that form as the flow disappears, you actually can minimize in that. There's something stronger, there's a stronger property they possess than a general singularity, and that's enough. There's enough there to exploit to actually prove that the least entropy of those guys is the round sphere. Okay, so that's, maybe I'll stop here and